This is part 2 of what I call a dialogue lesson on projectile motion. If you haven't seen part 1, this isn't going to make much sense, so get out of here and view that video first. Let's learn physics. Now that you've seen that, let's do a quick review. We did a cold intro to projectile motion. There's no pre-reading assignment. There was no flipped classroom video to prepare them, but they did have one entire semester of my physics class to get some of the big ideas pounded into their heads. They know Newton's laws of motion, and they have solved a lot of tough problems. And they've sketched free body diagrams since September. So I figured we could use that general knowledge of physics to analyze projectile motion. And it worked. We ended up with a lot of good summary ideas and free body diagrams and velocity diagrams. I assigned a reading between parts 1 and 2, so now they not only have general physics knowledge in that first introductory class, but some specifics on projectiles. Smart class, honors class. Let's get started. This is part 2. You, for today, you read some stuff, right? So now you know all about projectiles. Now you can pull that out if you want to, and you can just not take a look at it, or you can look at it, whatever you want. You can pull out those notes, because, you know, you take them for a reason. But some of this stuff is going to be things that you've seen before. It's going to be a review of what we did yesterday, an expansion into what we're going to do today, and a review of, well, essentially the entire first semester of class here, except for static equilibrium, because this or dynamic equilibrium and navigation. That's the only stuff we're not covering here today. Ready for the ball? Can you catch? Can you catch? You thought I was going to throw it there. Did you see that? That was nice. There was this one time when I threw the ball at the child, and as soon as I looked away from that child, he looked down to the cell phone and got smacked in the head. So, you know, I didn't want to. You ready to catch this one? Good volleyball, I like that. All right, so yesterday, review real quick. Forces. Tell me all about the forces acting on the ball as it flies through the air, Pete.
Its weight going down.
Well, that's it?
Yeah.
Well, yeah. As long as there isn't any what, Brandon?
Air friction.
As long as there is no air friction. If there's air friction, it's a little bit different. The air friction force. If, Matt, there were an air friction force acting on the ball as it flies through the air, as you see there, what would be the direction of the air friction force acting on it?
Opposite to tangential.
Opposite to the tangential.
Force. Velocity.
Opposite the tangential velocity. So remember, we're trying to differentiate again and again and again, starting in the first week of school. Velocity, acceleration, and force, constantly confused and confounded, and you just have to keep them all separate. So, opposite that tangential velocity, because friction force tends to, well, act opposite the intended motion, the idea. So we have that friction force would be acting. But why, Olivia, are we not going to pay attention to friction?
It's easier not to.
It's easier not to, and why else, Nate?
It'd be too difficult with it.
Okay, it's too difficult, it's easier, same basic answer, right? So what's another reason?
It's so little.
It's very little. So it's very, very small. For the objects, the small, relatively dense objects that we deal with in class, like this tennis ball, the friction force is really small. Now, when you get problems, eventually you're going to get problems in like the ball is thrown 300 meters per second. That's like 680 miles an hour. So it's funny. But there's going to be significant friction. But we have to ignore that because it's way too difficult. Because what happens, Eddie, as the ball moves through its motion, what happens to the air friction?
It would stay the same in theory if there were no.
But in reality, we're talking reality. In reality, what would happen to the air friction for something fast as it's flying through the air? Or doing that. Moving fast and far.
Would it decrease since the velocity, the horizontal velocity would decrease?
So is it slowing down on the way up?
Yes.
So as it slows down on the way up, is the air friction decreasing in
Yes,
size
it would be.
and in direction? Oh yeah, so we've got a problem here because also the speed, the air friction is directly proportional, approximately, to the square of the speed. So twice the speed, 4 times the air friction. 3 times the speed, how many times the air friction? 9 times the air friction. So it's this really complicated thing, and it's difficult to deal with. So we don't deal with it because, number one, it's really small for the objects we deal with normally, hopefully. And number two, it's just way too complicated. Now, velocity. What does the velocity do, Marissa?
Deals with speed and direction.
It is, yeah, so velocity, just general definition, it is a speed with the direction. So what, in this case, for a projectile, does the actual velocity do?
Ball change direction.
It changes direction and it changes
Speed.
both. So it's changing both speed and direction. Now your next diagram that you're going to draw, here you get the free body diagram, you get the velocity diagram, and those can be complicated up in a bit. 1, 2, 3 at the top, 4 over here, 5 over there. Arrows. Should you label these diagrams? Like label the arrows that you draw? If you label them, do you think you would like have a little bit less confusion? Like you're trying to label this thing and you're like, oh wait a minute, it doesn't, there's no force there. There's no, so label it, it does help.
Hey, Mr. Davis,
Hey Marcus, how you doing?
do you get personally offended when you're watching a sci-fi movie and the spaceships act like they're in the atmosphere?
If there's a spaceship and it's doing actually what it should be doing, it's really boring visually. Like really boring visually. So they do that to play to an audience. Do I get personally offended? No, I get really angry. I break things, but no, I don't get personally offended. Do you break things when you get angry? This is a conglomeration of all their diagrams. First, they had all that down arrows that are all the same size, and then they had arrows toward the center which changed in size, and look at that, they had some tangential arrows. Now, this is pretty interesting. And now that I reminded them, they started adding some of these labels. AWG 9.8 meters per second every second, 10 meters per second squared. They have to analyze. So get them to do it. They will eliminate the wrong answers one by one. What do you think about that stuff? What?
I was gonna say, well, it wouldn't be negative 9.8 because it goes up 2, so wouldn't it be 0? Or no? Never mind.
So you don't like the negative on the 9.8, or you just don't like the negative
I don't
9.8
like the
altogether?
negative. Wouldn't it be plus and negative or no?
Well, so if you drop the negative, how would you show the direction of the acceleration?
Okay, never mind.
No, well, what is the direction of acceleration?
Down?
Was it already shown up here?
I don't know.
Is it already shown up here?
Yeah.
Yeah, so do you need a negative and an accompanying arrow? No, the arrow is the negative, and the negative is the arrow. And the only reason we use negatives is to put them into algebraic equations so that we can deal with them there. It's preferable to use value and arrow, or value and an arrow, or value and an arrow. Arrows are better, because you build pictures in your brain. We really don't think in words. We think in feelings and pictures, really. So let's use feelings and pictures to get our ideas across. Draw lots of pictures and diagrams as often as possible. Tell them good stories. Engage their emotions. They'll learn and relate and remember better.
Well, there's no acceleration tangent. I mean, I guess they have a tangent to the curve, except on the left they have it like going backwards, and on the right they have it forwards. There's no force.
There's no force. There's no force in what direction?
And
There's no force tangent to the curve, so there is no tangential acceleration, correct? Wait, is there a tangential acceleration? Tangential acceleration. Allie, what is tangential acceleration?
It's the rate of change of tangential velocity.
Rate of change of tangential velocity, which is the tangential velocity changing? What?
Yes.
How do you know the tangential velocity is changing?
we put it on our other diagram?
Because it's on the other diagram there. Look at that. Oh, it is actually, is it changing speed? We have been through the acceleration of a projectile several times, but that does not mean that they understand it. They don't understand, and they can't explain. Just remember that they don't get it, and keep at it. Lots of exposures over the long term, and they'll learn. Because you know, and this is my terminology, nobody else uses it, but the tangential acceleration is specifically opposed to the, what other kind? Centripetal. You have tangential versus centripetal. The centripetal acceleration is all about the change in direction. And the tangential acceleration is all about the change in speed. Is there a change in speed up here? Yeah, there's a change in speed up there. So, is there actually a tangential acceleration? Yeah, it's changing speed. Is there a centripetal acceleration? Yeah, it's changing direction. So there is both a tangential speed and a tangential acceleration and a centripetal acceleration. And are both of those represented up here in that diagram? They are. So we have, and this is just, I just put all the stuff together that I saw there. Centripetal acceleration, centripetal acceleration, centripetal, toward the center. Okay, so that thing's toward the center, radially inward. And does this curve, is that a semicircle? Yeah? You know the shape. What's the name of that shape?
Ellipse.
Not an ellipse. It's not a semicircle.
Parabola.
It's unfortunately not a rainbow. It is, from your reading, it is a parabola. And this explains why it is a parabola in a minute. This is getting really confusing because isn't there also this thing here? Our standard diagram of force and acceleration for a projectile with everything just straight down works really well for our problem solving and for the standard approach that we use, but it does a disservice to the centripetal and tangential concepts we've already learned. We need both the standard diagram with only vertical forces showing the independence of vertical and horizontal, and we also need this diagram to show the tangential and the centripetal. Both of them help with understanding. What is the acceleration of this thing all the way through, and how do you know?
G.
It's G all the way through. How do you know it's G all the way through?
Because net force is equal to MA, weight's equal to mg.
You saw on the board yesterday. Yeah, so you have net force is equal to the mass times acceleration. That is Newton's what? Second law. Get Newton's second law. This is the weight. That's the only force acting, correct? Weight, and that is a down weight, is equal to the mass times the acceleration. Must the acceleration be in the exact same direction as the net force?
Yep.
Has to be. They have to be parallel. This is a vector equation, and so that acceleration is going to be down. And the weight, of course, this is m times g, the mass, times the gravitational field strength, which is, 10 or whatever, and that's down. And so acceleration is equal to g, which is 10 meters per second, every second down. So we know that that's the acceleration. If you had, and a bunch of you did, you just have this, that, and that, and you labeled it with, well, some of these things down here, some of them are better than others, then that's a really good answer. But down here is not good.
W.
W. W is a weight. And weight, Danny, what is weight?
Force.
It's a force of gravity, right? This is an acceleration diagram, so that's not there. How about acceleration? Is this acceleration? Yeah, but that's not, that doesn't help. You label the whole, this is the whole thing's labeled as an acceleration. Is this good? Can you label that as G, like down, 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 just those down arrows? Yeah, you can do that. How about 10 meters per second squared? 9.8 meters per second every second? Yeah, why do we use 10 rather than 9.8 most of the time? It's easier. And for 9.8, when do we use 9.8? It's real. We do real problems, real labs, things like that. We'll be using that next week. We do the one-shot quiz. Now we get to the philosophy behind the problem solutions. This part goes pretty quickly with all the background work that we've done, but it's still like dental work, since they still don't differentiate between horizontal and vertical, force and acceleration, velocity and acceleration, and now, this little thing right here, this is the acceleration. So I'm going to just erase these for now. Because you know they exist, right? There is a tangential acceleration and there is a centripetal acceleration, but this is what you start with, and this is the standard diagram that you will see everywhere. And this is an important point.
Wouldn't those tangential and centripetal accelerations be what you get when you break the gravitational acceleration into its components?
Yeah. So what are we going to do? You remember inclined planes, right? Inclined planes where you have like the parallel to the incline and the perpendicular to the incline. You take the weight and you exactly the same thing here. So you can do it with this one and you can do it with this one. This is the acceleration of gravity. Well, let's split it into the components. This is like, that's the tangent, that's the parallel. This is the perpendicular. All right. Here's a close-up so you can see that whole thing better. This is a complicated concept that, well, it's complicated. Connected to inclined planes. And if you haven't done inclined planes free body diagrams with your students, they're not going to get any of this stuff. But if you have, then this directly translates into that. Because if you take the weight and you split it into its two components, the weight is straight down and the component is perpendicular to the incline and parallel to the incline. And this parallel to the incline pulls it down the incline. That's the actual one that is the net force pulling it down the incline, unless it's balanced by a friction force. Anyway, this is the contributor to the acceleration down the incline. And this just, well, it doesn't really do anything other than push it into the incline and cause a normal force. So that idea then translates directly into this. And this works for both the weight and for the acceleration diagrams. I've drawn here just the weight diagram. Again, same thing, you get a perpendicular and a parallel component. And as you see with this parabola, it's curved the most at the top, curved the least at the two sides, and farther away you get from this vertex up here. And you see that the weight is the same size. Weight's the same size. Acceleration is the same thing. They're all just straight down. And if those accelerations are straight down, and this thing is moving in different directions, then you can take that and split it into its two components. There's a weight component perpendicular to the motion, perpendicular to the tangent, perpendicular to the tangential velocity, and a weight component parallel. And these two things do different things. The weight component perpendicular causes the centripetal acceleration, and the weight component parallel causes the tangential acceleration. This changes the direction, and that changes the speed. And as you get up to the top, you'll see that the weight component perpendicular is larger, and the weight component parallel is smaller. So as you get closer to the vertex, the rate of change of direction is largest here. Smallest here, smallest here. The perpendicular component causes that. And the parallel component is 0 at the top. So there's no change in speed at that instant. And the most change in speed at these two, farther away from that vertex you get. So here's the vertex. The farther away from that vertex you get, the larger the tangential acceleration, the larger the change in speed caused by the parallel component of weight. And the farther away you get from that vertex, the smaller the change in direction, the smaller the centripetal acceleration, because of the perpendicular component. That gets smaller farther away you get. Now what's the shape of these things? All those projectiles have a trajectory that, again, that is called a what?
Parabola.
Parabola. Have you dealt with parabolas in your math class? Yeah. What, Eddie?
I just bring back some good memories.
Oh, good memories. Good memories of parabolas. And then you put a different number in there and you subtract one, you add 3 and you multiply by the, what does this even mean? And it opens up wider and then it skinnies up and it shifts over to this side and it goes upside down, and those are the best. All those transformations for parabolas, it's the best stuff. Now does a parabola look like this? No, it doesn't. Parabola does not look like that. What does a parabola look like? Where's the most curvature? And if you flip that upside down, most curvature is like that. So most curvature right there. Why is the most curvature at the top of the parabola for that thing?
Because even though its horizontal velocity, or its horizontal speed is constant, its vertical speed decreases as it goes towards the top and increases as it goes down.
And at the top, at this very point right here, what is changing exclusively? Direction. All centripetal acceleration, only direction is changing here. Here, that g, which is the same as that g, which is the same as that g, here it's like, well, it's split into two components. It's turning a little bit, but it's also slowing down. It's turning more, but it's also slowing down a little bit less. Now it's all turning. And so all these diagrams that I've drawn with a nice smooth arc, they're not correct. These are not parabolas. They're just like half circles, which we like to draw. And it's really difficult to draw the parabola. But the reason it's this way is because at the top, you have the gravitational acceleration. And that gravitational acceleration is caused by the weight. Caused by that net force, which is the weight. And remember that these accelerations are caused by that thing right there.
It's a third law pair, so they have.
Third law pair, good. We don't call that an action-reaction pair, do we? We call it a third law pair. Tell me about it. Just tell me about it. I'm not going to throw it at you again.
Pushes the ball.
Hand pushes ball,
And the ball pushes your hand.
ball pushes hand. And they're balanced, right?
No,
Oh, nice. Why are they not balanced?
because they're going in opposite directions.
But wouldn't forces in opposite directions balance each other?
No, because it's on.
On the two separate objects, yes. So if they're on the same object, like normal force, weight, two forces acting on the same object, they're balanced. But again, Newton's third law, and we're going to use this when we get to momentum again. My hand pushes the ball, force on the ball pushes the hand, force on the hand. It feels like they're balanced, right? You can't use that terminology because they're on different objects. And otherwise there wouldn't be any acceleration. You know that when you really simplify it, it's just the weight. Just the weight, that's the only force. And then here, makes your hand dirtier and dirtier throughout the day, but then you only have the gravitational acceleration in the vertical direction. And if you only have the gravitational acceleration in the vertical direction, do you want to make this problem as complicated as you possibly can and talk about the changes in direction and everything else? When you could, and we did it here just conceptually, just to build pictures in your head and have you really understand the velocity and the acceleration and the force on a projectile. But we want to make problem solving and thinking about this stuff a little bit easier. So what's the direction of the acceleration, the only acceleration? Point. You're pointing? Why are you not pointing? Student participation is essential for their brain engagement and for my evaluation. Vectors are essential in physics, so I'm constantly having them draw arrows and point in the direction of a particular vector. They can hide their pointed fingers in front of them. It's quick. It gives you a good, fast, evaluative tool to direct the continued discussion. Pointing, the direction of acceleration is down. That is caused by the weight also down. That is the net force. Can you do the same thing that Marcus suggested and split this into its components? So here I drew the components, the x and y components. And if you know anything about vectors, the x component stays the same all the way through. It's exactly the same length arrow, and the y component changes. Okay, so what happens to the x component? What happens to that Vx as it goes through?
It's longer as it reaches the top and shorter as it goes down.
The x component?
Yeah.
Why? Because you're saying horizontally, it'll speed up and slow down horizontally. What's the direction of the only force acting on this thing?
Down.
Down. What's the direction of the only acceleration acting on this thing?
Down.
So, how much acceleration is there horizontally?
Wouldn't it just be, because it's gravity, wouldn't it just be 10 meters? 9.8 meters?
In what direction?
Down.
Down.
Yeah.
So does that affect this?
No.
No. So what happens to the x?
So the same the whole way through.
Same all the way through. So we have this thing being the same all the way through. The x and the x and the x, which is the whole thing at the top, and the x, all exactly the same thing all the way through, right? If you as the teacher are not flailing your arms to show The vectors, you're doing something wrong. It's weird, attention-getting, and highly demonstrative of the concept. We're going to use this in our problem solving. We can conclude that this Vx is constant.
Vx is constant. How's the parabola shape come into play?
Because,
Why don't we just talk about this?
hold on to that question. If the Vx is constant, what do you know about the acceleration in the x direction? Matt, acceleration in the x direction is?
Constant.
What is it? If the velocity is constant, what's the acceleration? The car is traveling down the highway at a constant velocity of 62 miles per hour. Zero. The acceleration is zero. Again, a lot of this is just like, okay, that word means this. Acceleration, velocity, force, continue to differentiate them in your brain. They still don't understand the vocabulary. Seriously. And these are good students, excellent students, and they confuse things all the time. Keep reviewing. That means that the acceleration in the x direction is zero. Which means, ask your question again, Michael.
What causes the parabola shape if the Vx is constant?
Therefore, what causes the parabola shape, that parabolic shape, if the Vx is constant?
The Vy.
The Vy. Does the Vy change? That's what's actually being changed. So you have exclusively a force in the vertical direction. That is the net force, which causes an acceleration in the vertical direction, which will take this y, make it smaller, and it goes to zero at the top, and then it starts increasing in the negative direction. So, if it's not constant, you can say it,
Is accelerating?
true, but we're talking like you're overcomplicating on physics terms here. So, if it isn't constant, you can say that it
Changes.
sometimes you want simple language. And sometimes you want them to use the official terms, switch back and forth. If you're all about the official physics words all the time, you're really missing something. If you're all about the simplest terms imaginable and don't use the official terms, that's kind of dumb too. If they are acting differently and if they don't affect each other, there's a good word we can use for the x and the y. That is
Vector components?
no. If they are anything, this is not just with these things, but if you have two variables that, they act differently and they don't affect each other, you can say that those two variables are independent. That's the independent. The x is independent from the y. And so what are we going to do? We're going to, because they are independent, we're going to separate them and keep them independent in our problem solution. The rest of this lesson is just a presentation on how to solve projectile problems. I've linked it here, so click on the video above or the I button to go there. I normally just go straight to the big ideas. X and Y independence and projectile behavior and example problems. Now that I did this, it's expanded my mind and theirs. It puts all of Newton's laws of motion and centripetal force and circular motion and gravitational field and all that other stuff together in one beautiful package. Next, we solved problems. A couple of days later, I wrapped it up. That's part 3. They will have practiced solving problems and are preparing for their one-shot quiz. See that? Thanks for watching Learn Physics. And thanks for that thumbs up, too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.